So now that we've talked just a tad about parallel streams, let's talk about some programming hazards that can occur when you use Java parallel streams. And this, again, will become more important when we do one of the upcoming assignments, assignment 3. So let's take a look and see what things can go wrong when you start doing parallel programming with parallel streams. Ideally, and this applies for both sequential streams and parallel streams, the behavior of the intermediate operations in a stream the output should only depend on the input it receives. So you want to be able to do things ideally where an aggregate operations behavior, like the map operation and something that's going to capitalize the first letter of all the characters from Hamlet or whatever, we want that to be side effect free. In other words, you only take in what you get through your parameters, you do whatever changes you need to make in terms of the implementation of the method, the behavior, and then you give a result back, and there's no side effect. You're not storing something in a global variable or a static variable. You're not putting something in a map, and so on and so forth. Ideally, that's what you would like. Here's an example, the capitalization example that we've talked about. You take a string, you see if the string's length is 0, in which case you return it, because it's really got nothing in it. Otherwise, you go ahead and you uppercase the first character, and you lowercase all the rest of the characters, and you return that. So that's a great example of a side effect-free method, or what's sometimes called a pure function. However, if you have side effects for whatever reason, and sometimes it's very hard not to have side effects. We'll talk about some situations where you need side effects. If you have side effects and you don't properly synchronize your behaviors in the context of a parallel stream, bad things can occur. And there's a bunch of bad things. One bad thing that can occur is called a race condition, which is kind of a funny name. But basically, a race condition arises when the behavior of the application depends on the sequence of the timing of threads for it to operate properly. In other words, you'll end up corrupting the values of shared mutable data or shared mutable state if multiple threads read and write from it simultaneously without it being protected by some kind of synchronizer. And I always, if you've learned anything by now, I love to visualize ideas. This is a race condition, smashing together, corrupting because they're trying to occupy the same space at the same time. Not a good thing. So that's one kind of problem that can arise. Here's a very simple example that illustrates this using parallel streams. Incorrectly, of course. So we're going to write a factorial method that's going to attempt to compute the nth factorial in parallel. Certainly a worthwhile thing to do. Not necessarily sure how much you use that in practice, but it's just to illustrate the point. And you can get this example in my EX16 project in the Java 8 folder in my live lessons GitHub repository if you want to run it. By the way, there's also correct implementations there too that use parallel streams just for comparison. So what we're going to do is we're going to go ahead and we're going to create a single instance of a class called total. And you can see that total has a field in it called mtotal, and we initialize it to 1. And it's got a method called mult that multiplies mtotal by n and updates mtotal. This is what's called shared mutable state. Why is it mutable? Well, we're updating mtotal. Why is it shared? As you'll see in a second, this variable, this local variable, is shared by multiple threads in the parallel stream we're about to write. So what we do is we're going to go from 1 to n using the long stream range closed factory method. It's a nice stream method that basically it's the equivalent of a functional for loop, if you will. And for each element in parallel, we're going to multiply t. So we're going to call t mult. So this method is going to be called to multiply mtotal by n and update mtotal. However, this is all taking place in multiple threads in the common fork join pool. So this mtotal times equal n is going to be called simultaneously in all these threads. And because there is no synchronization anywhere, chaos and insanity is going to ensue. And we'll have race conditions galore because there'll be multiple threads that are updating this shared mutable state without protecting it from simultaneous updates. So it'll be corrupted. And weird bad things will happen. And if you run the example in the EX12 program, you'll see exactly what happens. You get very strange results. There's also another problem here as well. It's less obvious. It's actually more pernicious because it's less obvious. there's this issue called memory inconsistency. And because we're not using synchronizers anywhere here, when we return mtotal is going to get called in some thread, and when it comes back, it could be inconsistent because it's also not being synchronized. So even returning mtotal could be a problem because you're maybe reading it from one thread that has not yet received the updates from all the other threads that are simultaneously updating that shared mutable state. And that's called inconsistent memory visibility, a much more subtle problem, much less likely to occur problem, but deadly nonetheless. Okay, so the thing to remember about all this is you have to be clever enough to avoid these problems. The compiler will not save you. This code will compile and run. The Java virtual machine will not save you. You have to be responsible for knowing what to do. Now, it turns out to be ridiculously easy to solve this problem, and the way you solve it is by using a different terminal operation, or different terminal operations, because there's multiple to choose from. So rather than using for each here, you would most likely use a method like reduce, or maybe collect. Reduce is probably more likely in this case. And reduce works perfectly fine with parallel streams, because it does clever things behind the scenes, which we'll talk about later, in order to ensure that we don't have corruption of the data. It uses magic synchronized portions where necessary in order to ensure there are no race conditions, in order to ensure there are no visibility problems. So that's just a quick overview of some of the programming hazards of parallel streams. Again, we'll cover this in more detail later once we've had a chance to talk more about parallel streams, but I want you to just be aware that if you stick with the stateless behavior of the parameters that are passed to intermediate operations and terminal operations, your life will be good with parallel streams. If you do not do that, then you can have these tricky problems.